Button. Hello everyone, welcome to today's instant of the GOCC. It's my pleasure to introduce to you Jonathan Boretsky, but before I hand over the stage to him, let me remind you all of the community statement with the 3 guiding principles. We are all learning, everyone has something to contribute, and no one has all the answers. With that said, please feel invited to ask questions either during the talk or in the end. And you can also ask in the chat, and one of the organizers will direct the question to Jonathan. Now, without further ado, Jonathan, please take it away.
All right, thank you so much. It's really nice to be here, and thank you so much for having me. I've never heard community principles like that at the beginning of an online seminar, so I really like those. Those are super cool. So thank you for that as well. And yeah, just to reemphasize, feel free to ask questions. Feel free to interrupt me. I'll try to keep an eye on the chat. If anybody asks in the chat and somebody else wants to interrupt to make me aware of that, that'd be welcome. But on to the math. So I'm going to be talking about the non-negative tropical flag variety and some fan structures. This is based on joint work with Chris and Lauren Williams. And there's going to be 3 parts of this talk. First, I'm going to tell you what the non-negative flag variety is, and in particular, what the non-negative tropical flag variety is. Then I will tell you a little bit about the geometry of non-negative tropical flags and give some characterizations of the non-negative tropical flag variety. And finally, I'll tell you a little bit about the fan structures on the tropical flag variety, and I underlined the S because there are a few, and I'm going to talk about how they compare to each other. So first, let's start with the flag variety. So a flag of subspaces, V, is a collection of subspaces in Rn such that each subspace is contained in the next one. So we've got to have that V1, or I should start from the empty set. The empty set is a subset of V1, which is a subset of V2, which is a subset, and so on, all the way up to Vm, which should be a subset of our entire space R to the n. And we should also have that the dimension of each subspace is tracked by the rank. So dimension of Vi should be Ri, where Ri is the ith entry of this rank vector. Okay, so why is this called a flag? If you imagine in 3 dimensions, or in 3 dimensions, you'd have a 0-dimensional subspace is like a point. Oh, and sorry, this should not be empty. This should be the 0, the 0-dimensional subspace, which is just 0. But you have a point, and then you have a line containing that point, and you have a plane containing that line. So there's our flag variety. All right, so that's the flag variety, and now I'm going to give you a more convenient way to think about it. So we'll say that a full rank matrix M represents a flag V if for each I from 1 through M, the first Ri rows of M span the vector space Vi. So here's an example of 2 different matrices, and let's think of them as flags of rank 1, 3. So the rank 1 component, we're looking at the span of the first row. So for both of these matrices, the span of the first row is just the span of the first unit vector. And then we're looking at the span of the first 3 rows. So in rank 1, 3, we look at the first row and the first 3 rows. If you look at the first 3 rows, this is, again, in both cases, easily seen to be the span of the first 3 unit vectors. They have zeros down the 4th column, but non-zero things in the first 3 columns. So as flags of ranks 1, 3, M1 and M2 represent the same flag. On the other hand, if you think of these as flags of rank 1, 2, 3, so now we also have to look at the top 2 rows, it is easy to see that M1 represents the span of the first 2 unit vectors, whereas M2 does not. It's got a 2 in that 3rd column on the 2nd row. So this 2 is causing us problems. So in this case, then M1 and M2 represent different flags. So all this to make the point that flags can have multiple representatives, and also the rank really does matter. So somehow the object we're looking at is the matrix, but the rank is somewhere in the background doing important work. All right, so this is a good way to think about flags. Let's keep refining how we're going to think about them. So if I is a subset of the numbers from 1 to n, we will look at the Plücker coordinate pi of m, And what's this going to be? It's going to be the minor of M in rows 1 through size of I and in columns I. So this is perhaps easiest to see through an example. So here is a matrix M, and we're going to compute its Plücker coordinates. So when the index is of size 1, P1, P2, P3, we want to look at the minor of our matrix, so the determinant in some rows and columns. And what are those rows and columns? Rows 1 through the size of I, so that's just row 1, and columns indexed by I. So P1 of M, we're looking at the first row, and we're looking at the column indexed by 1, which is just the first column, so that's going to be 1. P2 of M, we're looking at the second entry on the first row, 0. P3 of M, we're looking at the third entry on the first row, which is 1. All right, so those are the easy ones. Now we look at P1, 2 of M. So now the index is of size 2, so we're looking at the first 2 rows. And the actual value of the indices tell us which columns. So P1, 2 is going to be the minor of this 2 by 2, that 2 by 2 minor, which has value 1 in the first 2 columns. P1, 3, we're going to look at column 1 and column 3, and that minor has a value of 2. And finally, P2, 3 is telling us to look at columns 2 and 3. And if you take that minor, we get -1. Right, and finally, P1, 2, 3 is going to be just the determinant of the whole thing, first 3 rows, first 3 columns. And in this case, that should work out to -7, if I'm remembering correctly, / computing correctly. Okay, so these Plücker coordinates, if I give you a matrix, it's easy to get the Plücker coordinates. Now let me make the case that these are actually good coordinates for the flag variety. So I'm going to let V be a flag of ranks R, and I'm going to take 2 matrices M1 and M2, which represent V. We'll see that they. I'm going to claim that they represent the same flag if and only if Pi of, P. So the entire set of Plücker coordinates P of M1 is the same as P of M2, almost thought of as points in a product of projective spaces based on the size of the indices. Rp to the n juice 2 minus 1 ... Rp to the n choose n minus 1. Okay, so the Plücker coordinates should agree, except if you have all the Plücker coordinates with index of size 3, for example, you can scale all those Plücker coordinates simultaneously. If two matrices represent the same flag, if and only if these represent the same multi-projective point.
Can I interrupt you for a
Yes.
second? How does the rank go in this theorem?
Thank you so much. That is a great point. These should all be, so in some sense, which is the sense that I worked on at first, the complete flags where you have everything are the easiest ones. So I will sometimes forget to put ranks instead of putting everything there. So good. Thank you so much. But with that, let's look at an example. So here are 2 flags, which I claim represent the same, 2 matrices, which I claim represent the same flag. And indeed, if you look on this row over here, I'm multiplying all my Plücker coordinates by 2. And if I look at this row over here, where the indices are of size 2, I'm multiplying all my Plücker coordinates by 4. So by my previous claim, these do represent the same flag. And indeed, you can check that the row spans agree. The span of the first row are the same for the 2 matrices. The span of the first 2 rows are the same. And that's what we have to check because it's a flag of rank 1, 2. Right, so that's just a quick example of how that works. And with that, we can finally define the partial flag variety. So the partial flag variety of rank R, at least of type A, we're not going to worry about other types right now, or in this talk at all, is denoted FLRN. And this is GLN, the group of invertible matrices, modulo left multiplication by some block triangular matrices with some given block sizes. It's a lot of words to say modulo the operations which preserve the relevant row spans. Okay, so basically just look at equivalence classes, which are the matrices which represent the same flags. And then this embeds in a product of projective spaces, this time with the rights our eyes down here, as Stephen just pointed out. Sorry, is it Stephen or Stefan?
It's Stefan, but Steven is fine.
Sorry. As Stefan just pointed out, and this is going to be our variety. So good. What are some common examples? If we have a single rank, so if R is equal to K, well, then we're looking at subspaces of dimension K in Rn with kind of no containment conditions, because it's just one subspace. So this is exactly the Grassmannian. And when R equals 1 through n, as I was saying, this gives us the we call the complete flag variety, and we'll often just denote this FLN, and that's also a particularly nice case. One more thing I want to tell you about the flag variety, partial flag variety, is that it's cut out by these instance Pluker relations. I'm not going to worry too much about what the relations actually are, but I do want to point out that amongst these, there are some 3-term relations. And you'll notice that the relations are somehow depending on RT and RT prime, or these are 2 of our ranks from our rank vector. So where do you get 3-term relations? You get 3-term relations when RT equals RT prime. So these are called, or these are relations within a single rank. So these are the type of relations you'd get in the Grassmannian, for example, because there you only have one subspace. And you also get 3-term relations when RT prime equals RT plus 1. And this is when you have consecutive ranks. Okay, so this idea of consecutive rank will be important in what's to follow. So I just want to point out that one thing that's special about consecutive rank is that in these instance Pluker relations, you get 3-term relations. And it should be, I guess, kind of mysterious why that matters at all, but it's something I'm asserting is true and something I'm asserting is important. So that's largely want to tell you about the partial flag variety. Are there any questions up to here? All right. So now I want to tell you about the non-negative flag variety. But I need to tell you about 2 different notions of non-negativity. So we're going to have 2 different versions of this space. And we'll say the matrix M is totally positive if all of its minors are positive. And we'll denote the subspace of such matrices by GLN plus. All right, so for example, what would a representative element of GL2 plus look like? Well, it'll be a 2x2 matrix. And all of its minors need to be positive. So in particular, its 1x1 minors need to be positive. So its entries need to be positive. And its unique 2x2 minor also needs to be positive. So GL2 plus looks like this.
Just a quick clarification. This means actually positive, not just non-negative.
Yes, that's right. We're going to take a closure in a minute to take care of that. All right, so the Lustig non-negative flag variety of rank, I don't know what happened to my letters here. The Lustig non-negative flag variety of rank R is the closure, as I was saying, closure of the image of GLN plus in FLRN. So what are you doing? You're taking a totally positive matrix. It's a matrix with a positive determinant, so it represents some flag. And you can think of this flag as living in FLRN. And you take all such flags which are represented by totally positive matrices, and you take the closure, and that's going to be our Lustig non-negative flag variety FL greater than or equal to 0. So that's one notion of positivity. Another notion of positivity is to say, well, I gave you some coordinates. I gave you these Pluker coordinates. So let's look at the subset of FLRN where all these Pluker coordinates are non-negative. Okay, and this we're going to represent by FLRN delta greater than or equal to 0. So the first thing I want to assert is that these 2 things, and this definition is from Postnikov. The first thing I want to assert is that these are actually genuinely different things. So here is a matrix. It is Pluker non-negative. We can go through and compute the Pluker coordinates, which are P1 is just 1, P2 is 0, P3 is 1, so you just read across the top row. P12 is this 2x2 minor, which is 1. P13 is going to be this 2x2 minor, which is 0. And P23 is -1, which means I am missing a negative sign somewhere. Why am I doing this? Oh, I misread my own example. Sorry about that. So this is where ranks are very, very important. As I was saying, this is of rank 1, 3. So we have the Pluker coordinate of size 1 and the Pluker coordinate of size 3, P1, 2, 3, which has value 1. So we're good. This is a Pluker positive, Pluker non-negative. However, if I want to try to find but as I just pointed out, there is an issue. P23 is equal to -1. So there exists a negative minor. And the question is there a representative with all minors non-negative? Okay, and the answer is no. Let me show you roughly why. If it's going to represent this flag, it's basically got to have like the first row has to look like A0A. And then I've got some stuff down here, maybe like this. Okay, and the issue now is that P12 is equal to AB and P23 is equal to negative AB. Those can't both be positive, so you're always going to have some minor which is negative. So there's no representative of this flag which is totally positive, and so it's not Lustig non-negative. All right, so that's a great indication of why the rank matters. So what is the takeaway from this? We have these two notions of non-negativity.
Can I ask a quick question?
Yes.
So we take these non-negative matrices and we consider their images into these varieties, and so in general, I'll have one representative of the class be non-negative. Does that tell me anything about other representatives of the class? Okay.
No, it does not. So you can have various representatives that have different positivities. And I should point out also, once we're talking about these things, that when I talk about even the Pluker non-negative, which feels kind of perhaps better defined or better, structured, even here, because these are projective points, they actually have to have the same sign. They don't necessarily have to be positive, or within each of the multi-projective pieces, they have to have the same sign. So there's always some playing around you can do. But with the Lustig non-negative flag variety, as you're pointing out, it can be much more real. Like you can really have a lot of different representatives, which are not even kind of non-negative feeling. Excuse me. Okay, but the question that I want to pose is that it is easy to see that the Pluker non-negative part, the part where the Pluker coordinates are positive, is a subset of the Lustig non-negative part, because in particular, the Plukers are minors. So if the Plukers are all the minors are positive, then certainly the Plukers are positive. Or I should be saying non-negative, sorry. If the minors are non-negative, then certainly the Plukers are non-negative. Question is, when do we have the reverse inclusion? Okay, so we'll come back to this. Before we get there, I want to tell you a little bit about tropical algebra and the tropical flag variety. So the tropical hyperfield is the set R union infinity, and we're going to give it some operations. We're going to do tropical addition, which we'll denote with a circled plus. This will be the minimum of A and B. And tropical multiplication, which we'll denote with a circled times, is going to be A plus B, where that plus is normal real addition, and A plus infinity is always infinity. So this gives us some sort of structure. It's not quite a field. It's called a hyperfield, but it's familiar enough that we can do some examples. So 2 times 2 plus 3 times 0. So the plus is the minimum. We still respect the order of operations. So it's the minimum of 2 times 2 and 3 times 0. 2 times 2 is going to become 2 plus 2. 3 times 0 is going to become 3 plus 0. And this is the minimum of 3 and 4, which works out to 3. So this works, in a way that's not too unintuitive. it also works on polynomials. Let's take the tropicalization, this polynomial. All of our addition becomes minimization, addition or subtraction, we treat them the same. And all of our multiplication becomes addition. So the tropicalization of this polynomial is this, what we call a tropical polynomial. And that looks like this. And you can imagine if we put different values of x1, x2, x3, we'd get different results out of this polynomial, this tropical polynomial. All right, so given a tropical polynomial, it'd be nice to have a notion of a tropical solution. So we'll say that x is a tropical solution to a tropical polynomial if the minimizer occurs more than or equal to 2 times. So you've got some big minimum over a bunch of terms. If amongst those things that we're taking the minimum of, that actual minimum occurs more than once, we'll say we have a tropical solution. So looking back at this polynomial we have up here, there's 3 different ways you can get a tropical solution. The first would be if you have the minimum occur in the first 2 spots, x1 plus x2 equals x2 plus x3, and then the third thing was larger than those. Or you've got all the different permutations of this. So you could have the outsides be the minimum and be less than or equal to middle. Or you can have the last 2. Which is going to be less than or equal to x1 plus x2. So if we took, for example, the point 1, 1, 0, we'd have x1 plus x2 is equal to 2, x1 plus x3 is equal to 1, x2 plus x3 is equal to 1, and we find ourselves exactly in this situation. So this would be an example of a tropical solution to this polynomial. All right, so tropical solutions, that's good, but we want non-negative stuff. So let's talk about a positive tropical solution. And that's going to be a further restriction on the notion of tropical solution. We're going to insist that amongst the minimizers, so we have at least 2 minimizers because we have a tropical solution, but we're going to insist that one of those comes from a term which had a plus sign originally, and one comes from a term which had a minus sign originally. So if we go back to this example, one of our minimizers needs to come from these 2 with the plus sign, and one of our minimizers needs to come from this term which has the minus sign. Or another way of saying that in this case is that x1 plus x3 needs to be involved in the minimum. So in this case, a positive tropical solution needs to involve x1 plus x3 in the minimization. Or x1 plus x3 to x1 plus x2, which is less than or equal to the third option. Okay, so
a quick question. So does the minus sign here have any correspondence with how we might traditionally think of a minus sign? Because it feels like minimization, you can't undo that. So is the minus sign just kind of a formalism here, or does it actually behave in some way with addition like one might expect?
When we're talking about tropical solutions to a polynomial, the minus sign has no bearing. It only comes into play now that we're talking about positive tropical solutions. And I will tie this back to something more concrete in a couple of slides.
Okay.
Yeah, but we can see that this is a strong, this is a strictly stronger notion of solution because we have a subset. It's this and it's this, but that middle term is no longer a positive solution. Okay, so the next natural thing to do is that given a collection of polynomials, say P, we'll define the tropical variety, trop of P, to be the common tropical solutions of all the polynomials in P. So now we've got an idea of a tropical variety. And eventually we will build up the tropical flag variety and some interesting variations of it. But first I need to tell you a little bit about tropical varieties, just some basics. The first thing is that if P generates an ideal I, then unlike for regular polynomials, it is not true that the tropicalization of P, the tropical variety of P, is equal to the tropical variety of I. These are in general very, very different in the sense that one can be much larger than the other. And that follows through for the non-negative tropicalization as well. So if I take non-negative tropical solutions on both sides of this equation, I still don't have this equality. So this is very, very different from the way that normal polynomials work, where, of course, we have a solution to a bunch of polynomials. You also have a solution to anything in the ideal they generate. Whereas here, you really have to be careful if you're looking at polynomials for the ideal they generate. Let me give you an example of this. So here is two polynomials, x1 plus x2 plus x3 plus x4, and x1 plus x2 plus x5 plus x6. And here I collect their tropicalizations. The pluses become minimums, such as the minimum over each of the four terms in each of them. And here is a point x, which we can check satisfies each of these tropical polynomials. In particular, for both of these polynomials, x1 equals x2, they're both equal to 1, and it's less than x3, x4, and x5, x6. So these are properly tropical solutions. However, consider f3 equals to f1 minus f2, which is in the ideal. This is going to be x3 plus x4 minus x5 minus x6. And observe that x is not a tropical solution to f3 because x3, x4, x5, x6 all have different values for x. And this is kind of representative of the sort of problems you might run into where the terms that are the minima in the original minimizations can get canceled out, basically. So this is an important distinction to make and something we'll have to be careful of going forward. So as promised, let me give you a little bit of motivation for what these definitions are coming from and why these are reasonable things to think about. We are going to let curly C be the field of Puiseux series. So these are Laurent series in rational powers of T. And then we're going to let nu be a valuation which maps a Puiseux series to its leading exponent. So for example, if we took f of t to be this Puiseux series, 2 times t to the minus 2/3 plus I times t to the minus 1/3 plus higher order terms in t, well then nu would just return the value of the leading exponent, which is negative 2/3. Right, so this valuation map just gives you the leading exponent. And then we're going to look at a subset of the Puiseux series, which we're going to call R plus. And that'll be those Puiseux series that have a real positive leading coefficient. So this example I gave is an R plus because it has a real positive leading coefficient. Now, what's this have to do with the tropical hyperfield? Let f and g be two polynomials in R plus. Well, then the valuation of the product, the leading exponent of the product, is the sum of the valuations of the things you're multiplying. So if you have two polynomials, you multiply them, the leading exponents are going to add. And if you take a sum of polynomials, then the leading coefficient is going to be the minimum of the leading coefficients of the two things you're adding. The only time that this isn't true is if you have some sort of cancellation, but because I'm assuming that we're in R plus, which means that the leading coefficients are real and positive, no cancellation can happen, and this thing is true. So here, that's our connection to the tropical hyperfield. Here you can see where our tropical multiplication and addition are coming from. And then this theorem, which is the collection of two theorems really from Payne and from Spires-Williams, formalizes the connection. It says, let I be an ideal, and consider the variety of I in the Puiseux series and the positive variety of I, which is in the subset R plus. Then the tropicalization of I is exactly the closure of the valuations of the things in that variety, and the non-negative tropicalization is exactly the closure of the valuations of things in this variety, in this V plus. Okay, so I'm not. It's okay if this is still a little fuzzy. The idea is that they are intimately connected, and you can explicitly express the tropicalization in terms of these Puiseux theories using this valuation operation, but I'm not actually going to refer to these definitions further in this talk. So this is where it comes from, and why these operations are defined the way they are. But now let's actually get into it. Let's look at the flag variety and try to tropicalize it. So we're going to let PRN be the instance Plücker relations of rank R. So these are the relations which generate the ideal, which defines the flag variety, the partial flag variety of rank R. And we'll define the flag Dressian to be the tropical variety of these polynomials. And we'll define the tropical flag variety to be the tropicalization of the ideal generated by these polynomials. Okay, and as I cautioned, these are not the same thing. And in fact, for the flag Dressian and the tropical flag variety, they really are different for n as small as 4. You can start to see examples of differences.
A quick question. So when you say the instance-Pluker relations, that is just filling out your matrix with indeterminates and then doing your Pluker numbers?
Yes, that's one way to obtain them. I gave some explicit writing down of them earlier in the talk, but that would give you the same relations.
Okay.
Okay, so these are tropicalizations of the flag variety, but I'm really interested in non-negative tropicalizations of the flag variety. The good news is the definitions are easy to get when you're working on an iPad. I'm going to copy paste and I'm going to change colors, and I'll say the non-negative flag Dressian is the non-negative tropicalization. So look at the common non-negative tropical solutions, and the non-negative flag variety is similarly the non-negative tropicalization of the entire ideal. Okay, and these two things on the bottom are the objects I really want to play with going forward. So that is what we will do. All right, so here is a similar question to the one I asked a few slides ago. It's clear that the non-negative tropical flag variety is a subset of the flag Dressian, because the flag Dressian, it looks at the entire ideal instead of just the generators. There's strictly more relations to deal with on the bottom than on the top here. The question is, when do we get the reverse inclusion? There should be a question here. All right, so that's the second question. And the good news is I can answer both my questions in one fell swoop. So here are my questions again. The Pluker non-negative flag variety, the Pluker non-negative part of the flag variety, sorry, this inclusion is backwards. The Pluker non-negative flag variety is, sorry, no, it's not backwards. I need to have it that way. If all the minors are positive, then the Pluker coordinates are positive, and the tropical flag variety, as I just said, is a subset of the flag Dressian. When do we get the reverse inclusion? And the theorem, which comes from two places, from Block and Karp and from myself with Chris and Lauren, is that this is if and only if R is a sequence of consecutive integers. Integers. Right. So this in particular includes the example of the Grassmannian, where you have a single subspace, a single rank, a list of a single integer is consecutive. And when you have the complete flag as well, you get the same result. And I'll highlight that although the proofs are quite different, the proof that Lauren and Chris and I worked on actually would adapt quite nicely to the flag variety case. So in some sense, there is some unity going on here. There is some underlying structure that unites these two examples, these two proofs. And just to give a sense of what's special about consecutive R, well, here's what the three-term Pluker relations look like kind of in general, or one example of a three-term Pluker relation. When you take the positive tropicalization, you need to have the term with the odd sign out to be part of the minimization. So one way to write that is that PI union B plus, then don't worry about what A, B, C are or U, just to get the form down. But when you tropicalize, because that first term needs to be part of the minimum, you can write it like this. Okay, and the thing I want to emphasize here is not the subscripts, but to emphasize that the things on the left side are kind of uniquely determined by the things on the right side. So if I gave you 5 of the terms in the equation and left out, say, PI union B, you can uniquely determine it from everything else in the equation. And that's kind of special for a tropical equation. So if I scroll up to this one I had up here, for example, if I gave you x2, x3, x4, you can't necessarily uniquely determine x1. So that's this nice property that we're after, and that's what makes consecutive rank kind of special here. Okay, so that was the first big result I wanted to show you, but now I want to really dive into the non-negative flag Dressian and tell you a little bit more about it. And to do that, I'm going to have to introduce a few concepts. The first is the concept of a matroid. And a matroid is a combinatorial object which has many descriptions. I'm going to focus on two descriptions that are particularly interesting to me. The first one I want to talk about are the bases. So if I give you a matrix like this one, I can ask you to give me the bases, which are going to be the set of indices which are in n choose k, so there are k element subsets of numbers from 1 to n, such that pi of m is non-zero. All right, so in this case, we're looking at a matroid of rank 2 on n equals 4, so I want the bases to be the set of things such that the 2 by 2 minor in this corresponding columns is non-zero. So if I look at 1, 2, well, that's good. That's gives me a non-zero minor. If I look at 1, 3, also gives me a non-zero minor. 1, 4 similarly gives me a non-zero minor over here. 2, 3. Let me go away. 2, 3. We've got the same column twice, so that will give me a 0 minor. So I'm not going to write that one down. 2, 4 is non-zero. And 3, 4 is also non-zero. Okay, and you'll notice that really 1, 2, 1, 3, 1, 4, 2, 4, 3, 4, these are subsets, so I really should have curly braces around each of them, but I'm going to be lazy and not because I'm going to write a lot of subsets. And this is an example of a matroid. This is not quite a definition of a matroid. This is a definition of what we call a realizable matroid, which is a special type of matroid, which will be of particular interest to me. All right, but I do want to give you a general definition of matroid, so let me give a different definition, and that's going to be in terms of polytopes. So if you let EI be the standard basis vectors in Rn, and let I be a subset of numbers from 1 to n, we'll define E sub capital I to be the sum of the corresponding basis vectors. And if we let B be some set of subsets, we'll define the polytope of B to be the convex hull of EI such that I is in B. So take every element of this collection of subsets, take the indicator vector EI for that subset, and think of these as vertices with some polytope, take the convex hull, and that's going to be exactly P of B. All right, and then B will be called the bases of a matroid if and only if all of the edges of this polytope are parallel to some EI minus EJ. All right, so let me give an example of something which is a matroid polytope. So here I picked 5 subsets. In fact, I picked the same 5 subsets that I had up here. So you'll notice that I have 1, 2, 1, 3, 1, 4, 2, 4, and 3, 4. And I want to show that, for example, the edge between E14 and E34 is parallel to some EI minus EJ. Well, what's E34? I should take the indicator vector of 3, 4, so it should have 1s in positions 3 and 4. And E14, I should take the indicator vector of the set 1, 4. That should look like that. And if I take their difference, I should get, well, not should I do get 1, 0, minus 1, 0, which is exactly E1 minus E4. So it has the form that I wanted it to have. So this is an example. We have to check all the other edges, but this is an example of something which is a matroid polytope, which further shows that the thing we had above was a matroid. Now, matroids are great, but we need to keep going because I'm interested in flag structures. So I need to tell you what a flag matroid of rank R is, and they have similar descriptions. I'm going to give you a basis description and then a polytope description. So the bases, what I want to do is I want to look at my matrix, a n by n matrix, and I want to look at the rows corresponding to ranks Ri. So in this case, I'm looking at rank R equals 1, 2, 3. And I want to record the bases of the first row, the first 2 rows, the first 3 rows, and in general, the first Ri many rows, thought of as a matrix in and of itself. and then take all those bases together, and those are going to be the bases of my flag matroid. And again, these are realizable flag matroids. So it's just the data of one matroid for each Ri. If you take this data together, that gives you a flag matroid. Okay, so that's the basis description. Let's look at the polytope description. So if we have a flag matroid M, which is a sum of other, which is a collection of other matroids, like I said, a flag matroid, the data really is just different matroids of different ranks. Then we'll define the polytope of M to be the Minkowski sum of the polytopes of the matroids that make it up. We'll call them constituent matroids. And how do we know if this is actually a flag matroid? We'll say that this is a flag matroid if this Minkowski sum has all of its vertices equidistant from the origin. And this is a definition due to Gelfand, a theorem due to Gelfand-Serganova, that this is the same thing as being a flag matroid. Or a special case of their theorem anyways. So yeah, so we're going to have a bunch of polytopes, take a Minkowski sum, look at where the vertices are, and this will tell us whether we have a flag matroid or not. All right, so now we need to look at the positive version of these things. So I'm going to tell you what a flag positroid is. A flag positroid of rank R is going to be a realizable flag matroid of rank R, which admits a realization. So it has some matrix realizing it. So we're only looking at these special realizable flag matroids, but we want ones which have some realization where all the Plücker coordinates are non-negative. So this should remind you of the Plücker non-negative part of the flag variety, which we were talking about earlier. And indeed, there will be connections which we'll draw shortly. So let me give a couple of examples. If we look here, I'm thinking of this as a matroid of rank 2. I look at all the Plücker coordinates with index of size 2. P12 is 1, P13 is 2, and P23 is 1. So this is indeed a positroid of rank 2 because all those Plücker coordinates are positive. All right, so that's a non-flag matroid. Let's look at a non-flag positroid. Let's look at a flag positroid. 1, 2, 3 is the rank here. So if I calculate all the Plücker coordinates, P1 is 1, P2 is 1, P3 is 0, P12 is 1, P13 is 1, P23 is 1, and P123 is 1. Those are indeed all non-negative, so this is a flag positroid of rank 1, 2, 3. Now, there is a bit of subtlety here, so I'm going to point us down to this example. This is a 3x3 matrix, so it represents some flag matroid, and in fact, I'm going to look at the flag matroids here of rank 1, 2. And I want to look at the first row. The first row has positive numbers. It has all positive Plücker coordinates. So the first row is a positroid. The first two rows, the non-zero Plücker coordinates are 1, 2, 1, 3, and 2, 3. That's exactly the positroid we saw up here. However, when I write the matrix in this way, P23 is equal to -1. So that Plücker coordinate is negative. So the way this is written, this is not a representative of a flag positroid. And in fact, if we wanted to have a representative of this matroid, what we need to have something non-zero and positive in the first and third entries, because those are bases. And if we want a representative of positroid, the 1x1 Plückers need to be positive. And then you have to have some stuff in the second row, similar to an example I did before, some stuff in the second row, such that P12, which is AC, is positive, and P23, which is minus BC, is positive. But if A and B are both positive, this is impossible. So all this to say that just because you have a flag matroid, that this is actually a flag matroid because I have a representative of it, a flag matroid which has constituents which are positroids, that's not the same thing as being a flag positroid. The idea of flag positroid involves something a bit stronger. Excuse me. So that's just a caution. Now, one more thing I need to define before I get to my main result is the idea of a coherent subdivision. So let P be a polytope in R to the n, and we're going to associate a height vector HV to each vertex of P. And we'll consider a new polytope in R to the n plus 1, whose vertices are lifted by a height of HV. And then we'll look at the lower facets of P prime, which are those which have a normal vector pointing down with a negative last coordinate. And we'll project this back down to Rn. And the resulting subdivision is called a coherent subdivision. And this is perhaps best seen with the picture. So here is a very simple polytope. Okay, I'm going to assign a height to each vertex. And what you should imagine doing is you should imagine taking this, this polytope and pulling it out of the screen so that each vertex goes to the height listed next to its vertex. So you pull this vertex out a height of 1, this vertex out a height of 1, this height of 1, this height of 2. And what that's going to give you is going to be some three-dimensional polytope, and you should look at the faces on the bottom, kind of the faces looking closest to the screen, and project those back down. And what that will do is that will cut this square into two triangles like this. So you'll have this triangle, which is kind of parallel to the page in R3, and then this vertex is going to kind of be lifted a little bit higher, and it's going to break that parallelness and give you a different face. All right, so these are somewhat picturable in 2 dimensions. They get a lot harder to picture when you go up to higher dimensions, but that's all we're doing. And we're going to do it in arbitrary dimension. All right, so what coherent subdivision are we going to be interested in? We're going to look at mu, which is going to be a sequence of collections of coordinates, mu r1, mu r2 through mu rm, and we're going to think of this as a point in a product of tropical spaces, each of dimension n choose Ri. And we are going to let the mu rj underline be the set of indices of finite coordinates in mu rj. So mu rj is a point in T to the n choose Rj, and T is R union infinity, so it's going to have some finite coordinates and some infinite coordinates. So the support of mu rj, this underline notation, is going to be the indices of the finite coordinates. And then we're going to define P of mu underline to be the sum of the polytopes of each of these underlined things, where the polytope of a set of a collection of subsets is defined in the same way we defined the matroid polytope earlier. And what is this? Well, this is basically a matroid polytope as long as each of the mu ri's is a matroid. This is very similar to a matroid polytope. So just to get some sense of what's going on here, but it's some polytope. And yeah, so now we want coherent subdivisions. We're going to need to define a height function. And how are we going to do that? Well, we'll do it as follows. A vertex of a Minkowski sum is going to be a sum of vertices of the things that are in the sum. So P of mu is this Minkowski sum. So each vertex of P of mu is a sum of vertices of the P mu ri's, not mu rj's rather. And what are we going to do? Well, okay, we're taking different mu rj's, and we're taking vertices vij of each of these. Now, because mu is this tropical vector, it has a value at each of these vertices. And we're just going to sum up the relevant values of mu. So it's a little bit hard to track exactly what's going on, but it's some function which is combining data about the vertices of this P of mu in terms of this collection of tropical vectors. And once we get this height function, we can take a coherent subdivision and we'll call that subdivision d mu. All right, so it's not super easy to track what's going on here, but I can give you some examples at least. When n equals 4 in rank 2, these are examples in the totally positive part, the part where there are no infinities, the part where the support is everything. So the P of mu is the octahedron, and with this condition on the coordinates, you get the subdivision indicated here. And in the case of the complete flag variety, when n equals 3, rank 1, 2, 3, P of mu is a hexagon. And when you have this condition on the coordinates, you get this subdivision that's illustrated here. So that's something you can do. Now, in the case of, let's forget about the non-negativity for a second. Let's just look at general case. If you have a point in the flag Dressian, now this is not the non-negative flag Dressian, then Brandt and Zhang showed that mu is in the flag Dressian if and only if this subdivision I defined up there is a subdivision such that each face is a matroid polytope. Okay, so this was what we kind of knew going in and what we were trying to generalize. So somehow you can actually track information about your subdivision by knowing that something is a matroid polytope. So for example, in this case, this hexagon is a matroid polytope, as is this hexagon, and all the edges are matroid polytopes. So you'd be guaranteed that mu does in fact live in the flag Dressian. Not that any of that was obvious, but just an example of how this theorem works. So how are we going to generalize this to a positive context? So here's our main theorem. We're going to let R be a collection of consecutive integers, A through B. And we're going to let mu live in the appropriate product of projective spaces. And then the following are all equivalent. So 1 and 2 we've seen already. Mu is in the totally non-negative, is in the non-negative part of the tropical flag variety, and mu is in the non-negative part of the flag Dressian. So this we saw earlier. The third thing is that mu should satisfy the 3-term incidence fluke relation. So here's our 3-term relations making an appearance again. And we need to have that the support of mu is a flag positroid. So mu satisfies the non-negative 3-term instance fluke relations, and support of mu is a flag positroid. So it's almost enough to satisfy the 3-term relations. They tell you almost everything. You just need to make sure you have the right support. Another thing that's equivalent is that every face of d mu is a positroid polytope, so the matroid polytope of a positroid. And the fifth thing is that every face of d mu of dimension at most 2 is a positroid polytope. Okay, so being in the Dressian is equivalent to being in the tropical flag variety, is essentially equivalent to satisfying the 3-term instance fluke relations in a non-negative way, up to some concerns about the support, is equivalent to having every face be a positroid polytope, but actually only need the 2-dimensional faces to be positroid polytopes. Once you know that all the faces are going to be positroid polytopes. All right, so that's the big result I want to share with you. Now, it looks like I have 5 minutes left, so I want to quickly tell you something about fans, because I said I would. And there are actually 5 fan structures you might consider defining on the tropical flag variety. Let's focus on just a couple of them, just for time's sake. The Plücker fan is going to be a fan which puts 2 points of the tropical flag variety in the same cone if the minima in each 3-term tropical Plücker relation occur in the same places. So you've got all these 3-term relations, and if they're minima over these 3 terms, and if the things that actually give you the minima are the same for mu and for mu prime, then we'll say they're in the same cone of the Plücker fan. The secondary fan, we're going to look at the subdivision of P of mu. Look at the subdivision d mu of P mu. If d mu equals d mu prime, we'll say they're in the same cone. Okay, so these are 2 flag fan structures. There's more I could give you, but let's focus on these 2 for now. So what's known? In the Grassmannian case, these are the same for any Grassmannian. This is from Spire and Williams in 2021. And some, I didn't tell you specifically what these are, but I'll just say some names in case people recognize them. The Grosvenor fan, which is according to the initial ideal. You can take the common refinement of the Newton polytopes of a positive parameterization, which is, for example, would be a cluster chart. And then there's this more clustery one if you happen to have a cluster algebra. But yeah, so 1 and 2 agree for the Grassmannian, and the Grosvenor fan and this kind of clustery one strictly refine this secondary fan / Plücker fan, which coincide, but they are themselves incomparable. That's the Grassmannian case. Let's look at the complete flag case. For FL3, everything coincides. There's not much to say. For FL4, 1 and 2 are different. 2 refines 1. So 2 being the secondary fan according to the subdivision, the coherent subdivision induced by mu, and 1 being the Plücker fan according to where the minima occur. But let me just show you a quick picture. So the facets of this diagram are the different cones of the Plücker fan. And here is the subdivision. This squiggly line is this extra subdivision you get when you go to the secondary fan according to polytopes. So for FL4, we have a very good sense of what goes on. And so we get a full picture. We know that 1 equals 4, 2 equals 3, and 2 and 5 both refine 1 and are isomorphic to each other, but are not comparable. Whatever all those things mean, that's what's going on here. And I just want to finish with some open questions. So the big if is what happens when R is not consecutive, right? So everything I've said in the second half of this talk has been for consecutive R. What goes wrong when you don't have consecutive R? So some results fail. So for example, we know already that FL dr, the flag Dressian, R and the non-negative part is not equal to the tropical flag variety. Just yesterday, there was a paper that went up in the archive which studied the case of hollow flag matroids. So these are ones where the rank is 1 n minus 1. So that was pretty exciting. This was literally yesterday. And based on a quick first read of the paper, I think in this case, Olarte showed that the supports of points in the Dressian are flag positroids, which is not known in general. It's one of the harder parts of proving the results we did prove is to show that this is true when the ranks are consecutive. So this is interesting. Other things are open. So an example of something to be open would be pretty much anything about the fan structures. We know very little about the fan structures, even in the complete case. So even less about the fan structures in the non-consecutive case. And of course, there's this result up here, which I said is unknown. So that would also be open for the general case, although it is now solved for the hollow flag matroids. And another natural question one could ask is, what about other types? This is all in type A, and it would be really interesting to have a picture in other types. Although for now, there's no clear single notion of what there's no clear analog of each and every object I've talked about in other types. That would be an interesting direction to look in. And with that, I'll say thank you and ask if anybody has any questions.
Thanks for the speaker. So are there questions from the audience? Okay, so I do have a question. I mean, you stated as a question, but if you don't have consecutive ranks, what's going wrong in this theorem with all the things being equivalent? So do you still have some implications? I mean, some of them are kind of obvious, but
yeah, that's a good
what
question.
do you know there?
Right, so you still have some implications, right? So the tropical flag variety is always a subset of the flag dressing because there's more restrictions. There is a version of 3 which says that mu satisfies basically, and this would be equivalent to being in the flag dressing. So there's some version of 2 equals 3, which says something about the the three-term relations, and then like the relations of consecutive, not consecutive, but nearby ranks. Ranks are next to each other. So, sorry, I guess if R is R1, R2, Rm, something about the relations between R1 and R2, and R2 and R3, and R3 and R4. And off the top of my head, I can't remember what's known about these two in the general case.
Okay, thank you. More questions?
I had a question. So a little before the slide, towards the end of the talk, you're talking about realizing these. Well, I want to be careful. So it's when you start showing up, is realizing these tropical varieties as things like matroid polytopes, as polytopes. So it was not the fans.
Yeah, I scrolled the wrong way.
Yeah. So we have these coordinates, and you threw out the infinite points, and then you said, "Oh, these things will give us something similar to a matroid polytope." And I didn't quite follow exactly in what way is this similar to a matroid polytope.
Good. So it's similar to matroid polytope in the sense that if these things are matroids, if the supports of each of the MUIs are the bases of a matroid, well, then this actually like is a matroid polytope. It's a sum of regular matroid polytopes, and this is something that generally does. In the Dressian, for example, you're guaranteed that this will be a matroid and this will be a matroid polytope, and in the non-negative Dressian, this will actually be a positoroid polytope.
Okay. I guess the question is, the thing that's popping into my head is that there is a notion of something like a matroid polytope that's a matroid polyhedron. So it has unbounded directions, but they're a little bit different. So basically, well, what it is it's a generalized Bermuda So all of the edges are in the EI minus EJ. Its vertices are all 0, 1 vertices, but you can just extend some of these things out unbounded. And so these things are like the Bermuda version of matroid polytopes. And because you were throwing out the infinities, I was wondering if behind the scenes, you've actually taken an extended matroid Bermuda and turned it in, tried to turn into a matroid polytope. But the problem is when you cut off the unbounded direction, sometimes you don't end up with something that's a matroid polytope. Like you have to add in a couple extra vertices in order to do that.
Right. Yeah, it's an interesting question. I have certainly not thought about it in those terms, but that sounds feasible. Like somehow that'd be a nice interpretation of the infinities.
Yeah, I'm trying to look for if this work has been published or if there's a preprint of this work available or not. Because I've seen talks on it. It's new research though, so
that's cool.
Yeah.
Okay, it seems there are no further questions, so let's thank our speaker again. And we can stop the recording.
Right.